Hey guys, my name is Jason with Mount Baker Mining and Metals, and on today's video, I'm really excited because I finally got the assay results back from some tests I did about a month ago, trying to figure out the best way to recover the most gold and silver through the smelting process. And for those of you who haven't seen the video, I'm going to post it right after this shot so we can get all caught up and on the same page. Otherwise, you can skip ahead to see the results. We're going to take a deep dive into pyrochemistry and smelt down some of these gold concentrates. Well, here's a nice close-up look at these sulfides. These are gold concentrates off our shaker table, and they're primarily pyrite, and I think the gold is locked up within the pyrite crystals. And so no matter how fine you grind them, it's very, very small gold, and it needs to be smelted to release the gold. And we're going to get into the nitty-gritty details on this about what kind of flux I use, why I use certain flux ingredients and what they do. And we're going to test the concentrates. I'm going to get these assayed, and then we're going to test the slag after we're done to see how much gold we lost. And then we can get a real nice percent recovery from our smelting experiments. The first thing we need to do is take a sample of these. And there is a kind of a correct way to do that. And what I've read in the old books is you mix it like this, where you take a sheet and you just fold it in on itself kind of over and over and over again. And this is how you thoroughly mix up the sample so we can get a representative sample. The idea is to get the true value of what's in here and not skew it in any way. So for example, if I was doing something like shaking this all in a pan, all the gold would go to the bottom, and if I just took a sample off the top, then it would skew it as less gold than is actually in the sample. And so this folding technique is supposedly the best way to mix this. So I've got it pretty well folded up, mixed up. Now you can talks about quartering it in the books. So you quarter it, and then I will take a sample out of this pile here and this pile here and send those off for assay. I will combine the rest of this back together, and that's what we'll use for our smelting material. Okay, I'm going to call this sample heads number 1, and I'm going to take all the way down to the bottom, grab some of this material, try and get it all the way through the pile. And that will be our first assay. I'm going to do the same thing over here with this pile on heads number 2. Now these two are going to tell us how much gold and silver we have in the material before it's assayed. And that is going to be kind of our baseline for how much gold we can recover, and how much gold we lose in our slag, then we can figure out what our percent recovery was. Now what I actually want to test today is the addition of a collector metal. In the past I've used lead, this is bismuth, and I want to know how much collector metal we actually need to recover 99% of our precious metals. I did a test a couple weeks ago where I resmelted down some of my tailings, and I didn't get any metal collected at the bottom of the cone. And so I should have added collector metal, but I don't know how much to add. And that's what I want to test today. All right, so we're going to get down into the real nitty-gritty here. And I'm going to run a series of experiments today, but they're all going to have this same basic flux recipe, okay? So I want to go through this first, and then I'm going to talk about the details of how I'm going to change it and what I'm going to test. So every sample is going to have 100 grams of concentrates, which is approximately 1 mole of 50% iron sulfide FeS and 50% FeS2. I'm not quite sure which compound is in there, so that's kind of a good representation or good estimate. So that's what I'm going to use for the composition of the sample. So the main component of the flux recipe is going to be 100 grams of sodium hydroxide, also known as lye, and there's 2.5 moles of that. In the past, I've used sodium carbonate. I've switched over to lye, and we're going to talk about that a little bit later about why I made the switch. But for this experiment, that's what we're going to do. I'm going to add 20 grams of SiO2, which is silicon dioxide, which is quartz. there's about 1/3 of a mole of that. 20 grams of borax, which is about 1/10 of a mole. 25 grams of potassium nitrate. We're going to use this as an oxidizer. There's a 1/4 of a mole here, but what this does when it gets hot is it releases a bunch of oxygen, which will help oxidize some of these iron sulfides we have up here. Once all of this material is up to temperature in the furnace, comes to about 2,000 degrees Fahrenheit or about 1,100 degrees Celsius, I'm going to add 50 grams of iron in the form of nails. And once I add the nails, I'm going to smelt it for about 10 minutes after the iron addition to let the iron nails react with any leftover iron sulfide or FeS2. And what that is going to do is the iron, you've essentially flooded the system with iron. This is what we want. We want FeS because FeS is soluble in our basic slag, which we make up here. And when the vein or the fluid system was in place, in this situation, there was more sulfur there than there is iron. And what we need to do is we need to add more iron to push all of this over to this FeS. And when we get it all to FeS, it's soluble in our slag. If we leave it as this, you'll get a matte phase, and the matte phase is notorious for holding some of our precious metals. So that's why we add the iron in. And once we add the iron in, it's going to take a little bit of time for the iron to react with this FeS2 to pull those extra sulfur ions onto the iron metal and create 100% FeS. And so we're going to keep our flux and our cons all the same, and we're going to be testing how much material in the form of collector metal we need to recover all of our gold and silver from our smelts. The reason why I'm switching to bismuth is lead is pretty toxic, as we all know, and bismuth is really not. It's pretty benign. You actually drink it when you ingest Pepto-Bismol. And so bismuth is a safer metal. It's less harmful to the environment, and it has almost the same properties as lead. It has a very similar melting point. The oxides form a liquid at about the same temperature, so we can cupel the bismuth away just like we do the lead and leave the precious metals. So I'm going to switch to bismuth, and we're going to start using bismuth from now on in our experiments. So now we're going to get way down into the weeds and talk about the sodium hydroxide versus sodium carbonate. I've used both of these in the past, and I've done tests now to hopefully confirm that they both are equally good as a flux, and you don't lose more precious metals with one or the other. Now, they both end up being the same thing when you heat them, and let's go through that. So you have the sodium hydroxide plus heat goes to sodium oxide, which is what we want, plus water. Now the sodium oxide is what we want because that will help dissolve our FeS that we make from our concentrates. So you really want that sodium oxide, and it is produced in both of these reactions. The byproducts are a little bit different, but the important part here, and the reason why I like sodium hydroxide, is it melts at a much lower temperature. So this H2O is released before it gets super hot, and it prevents boil over. Also, you need less sodium hydroxide to create the same amount of sodium oxide compared to the sodium carbonate. You would need to add, I don't have the numbers off the top of my head, but it's about 1/3 more, I think, because the carbon and the extra oxygen weigh a lot more than the hydrogen does. And so I can get away with adding less of the sodium hydroxide, end up with the same amount of sodium oxide, and I don't have to fill up my crucible with a bunch of extra flux, and it doesn't boil nearly as bad as the sodium carbonate here. So that's why I'm using lye, and this is really what we're after, is sodium oxide. That's what we want. This is really expensive to buy. If you're looking just for sodium oxide, it's much easier to just add sodium hydroxide to your crucible, add some heat, and end up with molten sodium oxide in your flux. All right, I want to walk through mixing up the flux one time for you guys to see how this works. So I'm going to add our 100 grams of concentrates. This is where all of our precious metals are going to be. There's our 100 grams. This is our sodium hydroxide. We're going to add 100 grams of this. I should also mention the sodium hydroxide and the borax are both really good at absorbing water from the atmosphere. And the borax I'm using is anhydrous, so there's no water in it. If you go to the store and you buy it at the grocery store, you're going to get borax with some water in it. So you got to keep them in sealed containers. This is really, really caustic. It's really basic stuff. You don't want to get it on your skin, and you really don't want to get it in your eyes. It'll blind you real quick. So you gotta have, your proper PPE on when you're handling this stuff. I'm going to add our 100 grams of sodium hydroxide. Now we'll do 20 grams of silica sand. I add the silica for a couple different reasons. It's a great flux for oxides. It's very acidic. It makes it very glassy. And if you noticed when I was showing you the concentrates, they're rusty, right? They've oxidized some. So we need a flux in here that's good at absorbing oxides. Also, what silica does is if you're using fire clay crucibles, it protects the fire clay crucible from the lye, the sodium hydroxide. The sodium hydroxide, when it gets heated up, it really wants to grab onto silica, and it'll pull it out of the crucible, and it will essentially dissolve your crucible from the inside out. And so that's another reason why I add a little bit of silica, as it allows for the sodium hydroxide to attack the silica sand in our flux rather than the crucible, and it allows your crucibles to last a lot longer. Here's our anhydrous borax. This also is great at absorbing oxides, and it will help reduce the melting temperature of the silica. If I just added a bunch of silica in a crucible and melted it, it would not melt at the temperatures we're going to reach. So the borax absorbs oxides, reduces the melting point of silica, and also keeps the charge fluid when we pour it. So that's why we add borax. Here's our potassium nitrate beads. And again, this is going to act as our oxidizer. So when I heat it up, it's going to release a whole bunch of oxygen. And the oxygen is going to react with the FES, turn it into FeO, or some form of iron oxide. And it will also drive off the sulfur as some sulfur compound. And so it will help relieve some of that sulfur from our flux. So now we have our basic flux recipe, right? This is what we're going to do every time, every experiment. I'm going to put this in a crucible, and when it's molten, I'm going to add nails. For this first smelt, I'm not going to add any collector metal. We're just going to smelt it as is, and it's going to kind of be a test run to see if we can completely decompose all the sulfides. If we can't, I'll adjust the flux recipe a little bit. But also, is there enough metal in here to act as a collector metal itself and collect down at the bottom of our cone mold? Here's our fire clay crucible. Here is our mixed up flux. Comes up a little less than halfway. You don't want to get it right up to the top, because as this stuff melts, it does froth and boil and foam a little bit. And if you have it too full, it'll come over. I could use a smaller crucible, or I could get it up to about 2/3. But for this experiment, we're going to go with this. So now I'll go put it in my furnace, and we'll talk about the furnace just a little bit, and I'll show you the cone mold that we're going to pour it into. Here's our furnace. It's just KO wool wrapped in a cylinder. I've covered the bottom in Portland cement, just in case there's any spills. It's easier to clean up. And now we'll fire up our propane furnace, put the lid on, and we'll smelt it. Once it comes up to temperature, I'm going to pour it into this cone mold here. The metal, any metal that's in there, is going to go right down to the bottom of the pyramid, and all the slag will float on top as a molten slag, and then as it cools, we can pull it out of the cone mold, break off the metal tip of the cone, and recover our precious metals. While we're waiting for our test smelt to cool, I'm going to melt some of this bismuth. I need about 200 grams, 250 grams, that should be plenty. I'm going to melt this just in a crucible in the furnace. I'm going to pour it into water to cornflake it and to get a high surface area, small pieces that are going to act as our collector metal. And then I can add various amounts of collector metal to our future smelts to test how much I need for a good recovery of our gold and silver. Well, I'm going to try and get this bismuth down in that hot crucible down there. Let's see how this goes. There we go. That's already melting. There you go. That's going to melt quick. Here's our water bucket. You probably don't want to use a plastic bucket, but I wasn't prepared, and this is what we got. And then I got a board in here, and I'm going to pour my molten metal right under the water surface and hit that board, and that board will make the metal splat, essentially, hopefully while it's still molten, and it'll increase the surface area, and none should stick to the board, hopefully. So let's see what happens. Whoa. Well, that was kind of exciting. What do we got here? Yeah, there's a ton of surface area there. It's spread out like crazy. Well, let me get it drained and dried, and I might be able to even crush it up and use it as our collector metal. Well, there we go, crushed up bismuth. That worked pretty darn good. Huge amount of surface area. I just took a little hammer and just tapped on it and pretty much all fell apart. So now we've got a bunch of collector metal, and once we get our test smelt cooled down, we'll see if we have any matte. If we don't have any matte phase, then we'll continue and start adding small amounts of bismuth to our smelts. Okay, moment of truth. I screwed up and I accidentally dumped the nails into the cone mold. That's really not what you want to do, but we can break them out of there. But I don't know if you can see, I had to add 2 more nails because they got eaten so badly by all those sulfides in there. So there was a significant amount of extra sulfur in there that was eating away at that iron. Yeah, there's nails in there. So here's our slag. I can get it focused for you. pretty good looking. It's that stony look, which is characteristic of a basic slag. This is going to be a little bit deceiving, but right here is the tip of a nail and another tip of a nail, but there's no mat down there. A mat looks like a sulfide. That slag looks the same all the way down there. The mat looks a lot more crystalline. It'll have these crystals in it, so I'm real happy with that. That's a pretty good looking slag. I can smell the sulfur in it. It smells really sulfury still. But let's see, there's the slag. If there's any metal at all, it'll be down in the little tip of this cone here. Let's see if we got any metal. So I don't see any precious metals at all. I think we're home free. I wanted to show you I hammered those nails out of that slag, and you can see how they just get eaten up to nothing. I mean, there's one that's like a little needle, same there. The heads just get eaten down to nothing. This is the only full-size nail that was left. You can see right where it went into the slag, it got eaten up almost down to nothing. And I've edited the formula a little bit. I did 120 grams of lye, I did 30 grams of silica, and I did 30 grams of borax, and I took out all of the oxidizer because it tended to boil over. All right, so here's going to be our final recipe that I'm going to use. I'm going to use 100 grams of the sulfide sample. I'm going to use 120 grams of lye, 30 grams of silica sand, 30 grams of borax, and iron nails. And then I'm going to weigh each of the slags here. So our first one, no collector metal slag, weighs 285 grams. And I used 0G for 0 grams of collector metal with the lye as our flux. So there's our first sample. Let's crank out the rest. Okay, wow, I've been smelting for a long time here, but I got it finished up, and now I want to go over kind of the results with you. The first thing that I noticed, and I think I got some shots of this, is the bismuth is a real crystalline metal when it cools, and sometimes that makes it hard to separate from the slag, so you get little chips off the metal collector that ends up attached to the slag, which is not good. You really don't want that. Lead, because it's super soft, it's really easy to separate from the slag, but the bismuth is a little bit trickier. To go over our recipe, it's up here again. I use the same recipe for all of these smelts, and I'm not going to go over all of them, but here's the grams of collector. Here I used 25 grams and 50 grams as a lump, just a chunk of bismuth in the bottom. And then on these two smelts down here, I used soda ash instead of sodium hydroxide, and we'll go over that here in just a second. This is the weight of all the slags once the button was removed, and I'm just shocked about the variation in the amount of slag that we got. I have no explanation for that. We got 360 grams on one of the lumps, and we got as low as 238 on one of the collectors. So I do not know why the slags have such a high variation. This is the weight of the collector metal bead, the button. So on the 10 gram collector, I got 11 grams worth of button. On the 25 gram, I got 23 grams, and so on down the line here. And then these numbers here are the numbers I used for the assay results. Also, interestingly enough, most of the sodium hydroxide samples, even with the lumps, are almost exactly the same amount for collector metal as what I put in, with you know, a couple grams loss, sometimes a gain every once in a while. That's probably, like I said, you're getting little pieces chipped off in the slag. But when I added the soda, I started with 25 grams and it went down to 18. Now I may have lost some with the boiling there, but once I changed the recipe and made it so it doesn't boil, I still lost a significant amount, more than 10%, 12%, somewhere in there. This one I lost 20% or so, maybe more. So it's interesting to note that the sodium hydroxide has the best recovery of the collector metal, whereas the soda ash, you actually end up losing some, I don't know, through oxidation, or there's something that happens in the crucible with that soda ash where you're going to lose a little bit of collector metal. So it'll be interesting to see what the assays of these two come back with, knowing that we have some collector metal in the slag somewhere, maybe tied up with some sulfide somewhere. Now, because I had a little extra time and I'm doing this, I thought I might adjust a little bit. And so going back to these soda ash ones, I tried a couple different soda ash experiments. The 160 grams of soda ash should give us the same amount of sodium oxide as the recipe I used up here. But the problem is this ended up boiling. So this one up here, I used 25 grams of collector and it boiled. So it didn't, that's not a good recipe to use. I think there's too much soda ash there. So that didn't work very well. Then I did another one with 50 grams of collector. I used 100 grams of soda ash, 20 grams of silica sand, and nails. I removed the borax, and that one did pretty good. Good, no boiling. It foamed maybe just a little bit at the beginning of the smelt, but it quieted down real nice. And then I did another one here. Since that one did so well, I tried to match it with sodium hydroxide. Again, this will end up with about 62 roughly grams of sodium oxide, and 80 grams will end up with roughly 62 grams of sodium oxide. So since that one went so well, I tried to match it with the sodium hydroxide, 20 grams of silica, and it was like the perfect smelt. It was quiet, it didn't boil, it didn't froth, it didn't gain volume in any way at all. So that is like the perfect smelt. I ran out of bismuth on that one, so I only had 18 grams of collector, but what I ended up with I had 19 grams of collector metal. I ended up with 18 grams of metal and 228 grams of slag. So I sent this one off for assay. We'll get this one. This one is numbered 20 GCL over here. So then I did 4 more smelts. I tried back to the sodium hydroxide and silica sand, added a little bit more to match the sample. Tried adding some potassium nitrate. A little foam at first, but otherwise it was pretty good. It was a good smelt. So if you want to add a little bit of oxidizer, that would be a recipe to do that. Then I got curious and I thought, well, what happens if I added 100 grams of sample and just 20 grams of borax, which is real acidic slag, and some collector metal, and we didn't try and dissolve the mat, and we didn't try and make this perfect smelt. With this, you can get essentially the absolute maximum amount in a crucible without having all the extra flux. I ended up getting a huge mat layer here, and I'll show you. This is all bagged up ready for assay, but there's the mat layer right there. And I'm glad I got one so I could show you guys. It kind of turns blue, it's crystalline, I don't know how to describe it, but that's what they look like typically. And sometimes they're real shiny, but they're that crystalline matte. It looks like a massive sulfide, and then a little bit of slag on top. But if this works, and maybe we lose a little bit of precious metals to the mat, but if you can get 96% recovery instead of 99% recovery, then you can add 3 times what you could normally to a crucible, and you don't have to do it all 3 times and waste all the fuel and all the time and all the stuff. So this is going to be an interesting one where it's just essentially a very poor smelt, but maybe having a small amount of loss is okay if you can cram 3 times in as much and get a decent recovery. And look at this button separated super, super nice from the slag. It didn't break up. It's all nice and contained there in the metal button. Then I did a couple more down here. None really worked. I tried to flood the whole system with potassium nitrate, and it just frothed and foamed and boiled all over the place. And then I reduced it down to 50, and same thing, it just boiled too much. So you really got to be careful on how much oxidizer you add. But in a nutshell, that is the results from all of our different smelting tests. Okay, so our next step is I got to get all this stuff off to the assayer and get it professionally assayed so we can figure out our percent recovery. And then I'm going to take all those beads that we got and I'm going to put them in the Cupel furnace and I'm going to refine them down to just the precious metals, just the gold and silver. All right, so we're going to just jump right into it here and start throwing out samples. Here is one of the prills that we got. So now to get the gold and silver out of here, I'm going to put it in this Cupel. I'm going to put it in an electric furnace where it gets up to about 1800 degrees Fahrenheit. And when that happens, the bismuth and any other base metals in there become molten, as well as the oxides. And the oxides will form a puddle on top of that molten metal, and they'll shed off the puddle and become absorbed into this Cupel. That process continues until only the precious metals are left. And when that goes to completion, you end up with a little precious metal bead, just like this one here. And so this went through the process. It started out like that. All the base metals turned to oxides and were absorbed by the Cupel, and the little tiny precious metal bead is all that's left over. So we've got a bunch of samples to work on. Let's get started, and I got to get them all labeled so I don't mess them up and screw them up. But we're going to get all of our prills refined down to just the precious metals, and then we can do some analysis on them.
All right, we'll try this. So I've got 3 different cups here that have the different samples we're going to be running. I've preheated my Cupels. Now I'm going to put these There's that one. So I'll put that one in first. Okay, don't dump that all over the furnace. That's what we don't want to have happen. There we go. So there's all our samples. There's 3 samples. There's their tags, left, right, and middle. So now we'll let those work and see how big our beads are. All right, we'll have a look here at our first 3. Yeah, there they're going. The 2 on the left have 50 grams and the one on the right has 25. So the one on the right will be done sooner. We'll swap it out for another one. All right, we'll take another look here. Oh yeah, we got 2 done. So we'll put these again in order. There's 1. There's 2. Gonna put another Cupel in to start warming up. And we'll let that last one finish up.
Here's the beads from all of our samples across here. And now what I'm going to do is take each bead from each Cupel and weigh it on this scale that goes down to 0.001 grams. And a little trick for you guys that I've found is if you have some weight, a lot of times these really tiny little beads, they don't register on the scale or you get a little inaccurate weight. But if you put weight on the scale and tear the weight, well, it just went off now, but if you tear the weight on the scale, you get a much more accurate measurement when you weigh a very, very small bead. So I won't make you watch every one of these, but I'll weigh each one of these and then I'll put them down here and then we can go look at the assays and figure out our percent recovery. The other thing I'm hoping we can do now that we have our assay results is we can figure out how much gold and silver are in these beads. And I've always kind of just winged it based on color. But now that we'll be able to have a definitive number, we can hopefully back calculate and figure out how many grams of gold and grams of silver are in each of these beads. And then we can figure out what that looks like based on this color. I'm gonna guess, I haven't looked at the assay results yet, but I'm gonna guess that these are about 75 or 80% gold by weight. Since we're here, I'm gonna try out my new little microscope. It just clips right on my phone. I've got all our gold beads right there. Let's see what they look like under the microscope. And here we're looking at all our beads. And it's quite surprising that the finish is not equal on all of them. The one in the lower section there is real nice and shiny and smooth. But a lot of them are real matted. That little tiny one down there is also real nice and smooth. But I wonder if that's because they didn't fully cupel. There might be another 1, 2, 3% of base metals in there. So that's kind of interesting. But it gives you a real good idea of the color. And the shiny ones are mostly gold, or more gold color than the matted ones for sure, which are more silver in color. Anyway, just an observation. Thought it'd be cool to look at them under the microscope. I also get a lot of questions through email and comments on the YouTube channel about what I use when I do my smelting stuff, the scales, the crucibles, the fluxes, that kind of stuff. So I've left links to everything I use down in the description below. So if you're interested in stuff that I use or you want to get some for yourself, check those out and you can buy it right through those links. The other thing we've done is we've created a Patreon account so viewers like you can help support us with buying propane, flux, all the components, everything that goes into making these cool videos that you guys like to watch. So if you would, please check out our Patreon account and support us if you can. We're going to jump right into it here. This is the assay report I got back. Here's the gold and the silver in ounces per ton. Obviously, here's our sample IDs. And unfortunately, like I said, it's in troy ounces per ton. And I like to do all my math in the metric system, so we got to convert them into parts per million, which is also grams per ton. So you take the ounces per ton, and there's 31.1 grams per troy ounce. So when you multiply those numbers across with 31.1, you get those two numbers. So I'm going to work these down, but one of the first things I noticed right off the bat when I got it is there's still a lot of gold left in our slag, like way more than we want, and silver as well. So I'm a little bit concerned that we didn't get the recoveries we wanted, but we're going to go through and do our calculations and see what kind of percent recovery we got. I've gone through and I've graphed all the data now, and I wanted to talk about there's 3 different ways that I can analyze the data that we have. The first one is probably the most straightforward and easiest to do a percent recovery study on. And of course, my printer ran out of ink as soon as I needed to print in color, so my daughter lent me her crayons and I colored in the lines here. So the blue is percent gold recovery, the orange is percent silver recovery, and this graph is the heads assay versus the tailings assay. And I'll do some sample calculations here in a little minute so you can see how I calculate each one. But this along the bottom is, I've ordered these in order of least amount of collector to most amount of collector. And other than this one, this is kind of out of whack here, there's kind of a trend line here, both with gold and with silver, showing the more collector you use, the higher percent recovery you get. Now the problem is, even on our highest percent recovery, I think this is like 91% recovery with gold, that's still not as much as I was hoping for. I was hoping for at least 99%. So I was really disappointed with these results, actually. But this is what we got, and I'm just reporting the data that I have. So there's the results of our heads versus tailings assay. Let's look at the other two. Now we're going to look at the percent recovery based on the bead weight, the weight of the bead versus the heads assay. And what I did here, again, sample calculations coming at the end, but I took the weight of our bead and I added together the grams of gold and silver in the heads assay. And so I can calculate how much grams of precious metals we were supposed to get based on our bead and how much we actually got. So this is, again, percent recovery of the weight of the bead. The axis along the bottom is the same as all these graphs are. And again, this clear trend line of the more collector metal you use, the higher percent recovery. And on this graph, it shows once you get up to about 50 grams per ton, you get a really good recovery. This one's actually over 100. We recovered more precious metals than there was, quote unquote, supposed to be in the sample. And then actually the 100 grams of collector fell off. This is again about 85 or 90% recovery. So this shows that as long as you can get up to about 50 grams collector metal, you should be recovering 90% plus of the precious metals in the sample. If you stop at 25 grams, which is about a quarter, you only end up recovering about 50%. And the reason why this doesn't have gold and silver is because all I have is a bead of precious metal. I can't split it into gold and silver. So this is again just calculating the weight of the bead versus the cumulative weight of the assayed gold and silver. And then the last graph that we have is the bead weight versus the tailings assay. And again, a very similar trend line. Again, the axis is all the same, but the trend line is the less collector, the lower percentage, all the way over to the more collector, the more percentage. Now this was a little bit more interesting because based on the tailings assay, the amount of gold left over in the tailings, we recovered much less here. The 50 grams collector metal per sample only recovered about 75. And then look here, this 25 grams of collector, I think that means blob with the mat in it, had a pretty high recovery. There was not much precious metals in the tailings. So that was kind of interesting. But then here again, you see this 100 grams of collector is back up to about 85 or 90% recovery there. And here's just a really quick shot showing all three graphs at the same time so you can compare. But again, over on this right-hand side, on all three graphs is where we had the most gold recovery. So now let's go take a look at some sample calculations. Well, now we'll go through the sample calculations I did to come up with our numbers. This is going to be a calculation of the heads assay versus the tailings assay. And I'm going to use the example of 50 GCL sample to do it. So the first thing you got to do is convert your ounces per ton into grams per ton. So you take that, that's the assayed value, multiply it by 31.1. That's how many grams per ton was left in the slag. Now we got to convert the amount of slag we have into tons of slag. So there's 307 grams of slag that we weighed. There's 1 million grams per metric ton. So when you divide those two, you end up with 0.000307 tons of slag. So that's the slag number we have. And now we can figure out how many grams of actual gold is left in our slag based on the tailings assay. So you take your metric tons of slag multiplied by the grams per metric ton that was left in the slag based on our assay, and we have 0.00496 grams of gold that's left in the slag. Moving down, you go to the head sample. The head sample assayed 0.02286 grams once I've done the calculation that we saw up here. So that spit out this number per 100 grams. So when you take the grams of gold in the slag divided by the grams of gold in the head assay multiplied by 100, you end up with a 21.7% loss, or if you invert that, a 78.3% gold recovery. So that's a sample calculation of how I came up with the head assay versus tailing assay percent recovery. And it's really amazing how often I reference these videos that I've done when I'm working on new projects in the future, because I have to make sure that I'm doing all my samples the same way and my calculations the same way. Let's move on to the bead weight versus the head assay. This is a little bit easier calculation because we have the bead weight. This is both silver and gold in the bead. And so we're looking for our percent recovery. You got to figure out the total amount of precious metals in our assay. So again, using some calculations to figure out how much grams of gold and silver is in our head samples. Then we add those two together. The total amount of precious metals is 0.03878 grams in our head sample. Here's a little sidetrack here. We're going to calculate the amount of gold and silver in our sample. So when you take the amount of gold divided by the total amount of precious metals, you end up with 59% gold and 41% silver. So that was a question I asked earlier in the video, and this was a really easy time to calculate that. But now we're going to keep going down here, and our bead, which is 0.035 grams, you divide it by the total amount of precious metals that came out in the assay, and you come up with 90.2% recovery. So this is a good way to check what you can recover versus what's supposed to be in there. Now the last one is the bead weight versus the tailing assay. So again, the bead weight's the same. We figure out how much gold is in the tailings, and you convert your assay of slag to total grams of precious metals. So I calculated that off camera here. So we ended up with 0.01165 grams of precious metals in the tailings or in the slag. So you divide your bead weight by the bead weight, that's what you recovered, plus what is left over in the slag. So you end up with a 75% recovery. Now, talking about these two together, this is a good way to figure out what was recovered versus what you supposedly had based on your head assay. This is what was recovered versus what you lost. And this one here, the heads assay versus the tailings assay, takes the bead weight completely out of it. It really doesn't matter how much gold I recovered. It's just much more of an empirical way of calculating, okay, we got a head assay result, we got a tailings assay result, and regardless of how much gold I got out, it's just how much we started with and how much was left over. So this is probably the most accurate way, because over here, when we're doing the bead weight, there could be some base metals left in there. Maybe I lost some when I was cupelling, but this is really whatever I did in the middle doesn't matter. It's the professionals did the head assay, and whatever I sent them in the waste or the tailings, they did another professional assay and got the 2% difference. But sometimes it's good to look at all three different ways and see if they all line up. It's kind of a double check there. Well, guys, I'm a little bit baffled. I'm really surprised that our recoveries aren't higher. 85, 90% at the best is still not very good. Like I've been teasing you, I have some video I'll put right after this shot showing you some tests I did 3 or 4 years ago probably, that I got really, really good recovery, 99.9% recovery of the gold and the silver on a few of them. And so I know it can be done, and I'm not quite sure what the situation was that prevented me from doing that this time. Take a look. I have an idea, and I'll share that with you on a future video. But take a look at this next shot and let me know if you can spot the difference in the situation. Leave me a comment down below. There's definitely going to be more videos coming out. I really want to be able to do a smelt and recover a very high percentage, 95, 98% plus of the gold and silver. And right now I'm not able to do that. And I think there's two different things going on there. I think one of them is that the amount of gold in the samples is low. You would not be able to production smelt this and make any money. You just can't pay off the fuel and the time and the flux and all that stuff. So this is really more of how you do an accurate assay than how you production smelt gold. I think if you had thousands and thousands of grams per ton, I could do a really good job of recovering a high percentage. So we might have a little issue on the amount of gold in the samples. So let's take a look at this next shot and see if we can figure out the difference. Here's the material we're going to be experimenting with. This is some high-grade concentrates off the shaker table. On all of the charges, I'm going to be adding metallic iron in the form of, I think I'm going to use a piece of steel flat bar, and I stick it right down the top of the furnace, right into the crucible, and that way the iron will reduce any of the other metallic components, lead, copper, into metallic form, and they will precipitate hopefully down through the slag and collect in the bottom as metallic metal, either in the collector metal that we use or as a button if we don't use any collector metal. Okay, so we've added our 3 components to our flux here. We've got 100 grams of number 1 shaker table concentrates in the bottom. I've added 150 grams of soda ash, 30 grams of silica, and 30 grams of borax. I'm going to take it, put a lid on this, shake it up, mix it up real good. And we keep the flux really basic because the basic flux will absorb the FeS, the iron sulfide that we create by adding the metallic iron to this material as it fluxes. So if there's any galena in here, the PBS will convert to FeS and the result will be metallic lead that will then fall down to the bottom. Okay, we just put our charge in. I've got a piece of rebar sticking out the top of the furnace. See the crucible down there? It's just starting to glow a dull red, so I just added the charge. And I'll let that, it'll probably take about 10 minutes to fully melt, and then I'm going to fuse it for maybe another 10 or 15 minutes. Okay, so we've got our stuff all up to temperature. It's not forming a bunch of bubbles. It's all nice and quiet now. So we're going to go ahead and pour it into our preheated cone mold. I'm going to add my copper for our next experiment. Here's our next round. Here's our cool down slag, and we're going to knock that out of the cone mold, and we'll see what ended up being reduced on the bottom as far as metallics. Okay, so I just take my cone mold, I turn it over in my metallic bin here, give it some taps with the hammer, and usually the slag comes out. Yeah, there it is. So there's our slag. It's probably still hot, but this right here looks like our, yep, so there's our metallic button. And again, this was just adding iron to our basic flux and our 100 grams of stuff off the shaker table, and we ended up with a little metallic button. So we reduced the less reactive metals than iron by putting metallic iron into the mix. So here's our little metallic button from our first experiment. And it's not quite cleaned up. There's still a little bit of slag on there, but it looks like from 100 grams, we ended up with 18-gram button in the bottom. So that's actually pretty good. All right, so this is our first sample of the collector metal. We used copper. Oh, it came out as a nice piece. So there's our collector metal that all came down to the bottom. We added 100 grams of copper, high surface area copper. You can see on the slag, it's fantastic separation from the metallic section from the slag. There's no beads of copper or anything in the slag left there. The slag is nice and hard and competent. The metallic section is flat on the top. That's just about as perfect as it gets. Also, I wanted to point out one more thing. I broke our slag apart, and you can see there's no mat at all. There's no mat layer. So the basic slag did its job. It absorbed all the iron sulfide that we made, and really came out just, I mean, that was a beautiful pour. That really worked very nicely. All right, for this next experiment, I'm going to use silver as a collector metal instead of copper. All right, I just poured our first silver test. And you can see there's our silver collector metal at the bottom of the cone. All right, here's our silver button collector metal. We ended up with 108 grams. So we started with 94, so that's 14 grams of additional metal was collected by the silver collector. Okay, we just knocked our lead charge out of there. And it might be hard to see, but there's a lead button at the bottom of this one. So I had about 1.5 kilograms of shaker table concentrates that I used the same slag or the same flux recipe for all of these samples, and the only thing I changed was the collector metal. But I took out 2 separate samples of the shaker table cons, so we're going to send these off for assay. That will tell us how much gold we have in our sample that we started with. The first test I did, and all these are duplicates of each other, the first test I did 2 samples exactly the same of no collector metal. So I used my flux recipe, added iron to reduce all the metallics above iron on the reactivity chart, but we ended up with 2 little buttons with no collector metal used. The second one we did, I took high surface area copper and mixed it in with the entire charge, 100 grams of copper. The second one we did was we just added 100 grams of copper right to the bottom of the charge. We put it right in the bottom of the crucible. The next one we did was we used silver, used 3 tray ounces of silver, ended up being about 94 grams of pure silver, and I used the button twice and put it right in the bottom of the crucible. The last one was I used lead, and I put 100 grams of lead in the bottom of the crucible, put the charge right on top, and we used lead as a collector. So there are all of our different samples. I'm going to send the slag of all of them off for assay, and the slag will tell us how much gold and silver is left over after the collector metal was used. I've really gone back and forth with myself about if I'm going to crush up the slag and see if there's any metallic beads left over in the slag, and if there is, should I get those out because it will contaminate the assay. And I am not going to crush up the slag. I'm going to send it as is. The reason we're doing all of this is because I want to know the best way to go about collecting the most precious metals the easiest possible way. If you need a high surface area collector metal that is throughout the charge that trickles down through, that's okay. We need to find that out. If you can just put a slab of metal in the bottom and have it collect through contact with the convection going on in the crucible, if that works, great. If silver works better than copper, we'll know that. If lead works better than copper, we'll know that. So this is a first pass trial run to figure out how much gold and precious metals we can recover through smelting without roasting and by using iron as a reducer, and then we can assess which collector metal does the best job. So I'm running out of material. I've got, I don't know, 150 grams or so left of the ore, and I wanted to try something a little bit different. Rather than adding a collector metal or iron, I mixed 50 grams of the shaker table concentrates with 300 grams of Chapman flux, and then about 100 grams of borax to help thin it. And my goal here is to see if I can recover any gold button at all by oxidizing the base metals and see if we can get a little tiny gold button at the bottom. Okay, here's the slag result from our Chapman flux. It's really quite glassy. You can see there's no obvious metal at the tip of the cone, so I'll bust that open and see if we get a little tiny gold bead, which is what we hope for. So I busted the tip of that cone out, and sure enough, there's a little bit of, I think it's actually a matte button. Okay, so I busted out the matte, which is here, a little tiny bit of matte. Ended up with these 2 little buttons. There's one and there's one. And there are these 2 little tiny buttons. I don't think they're pure gold. They've got some coppery color to them and maybe a little bit of lead. So if I can get my friend with the XRF gun, I'll zap these and see exactly what we have here. The matte is a little bit troubling down here. You really don't want matte. It'll dissolve silver especially, and so if we had a bunch of silver, it's probably ended up in the matte there instead of in the metal buttons. But I'm going to send that slag off for assay and see if there's any precious metals left in the slag. If there's not, we have all of our precious metals down here in the mat and the little bit of metal we got at the bottom. So this is actually pretty encouraging. So with the results from the assays and the XRF, we'll know where most of the gold went on this one. Okay, so here are the results from our assays. And before we get into them, I'm going to go over a few things. This axis here is the percent recovery. It goes down to 70. This axis along the bottom is the different collector metals we used. And the yellow line is the gold recovery. The gray line is the silver recovery. And even though I ran 2 samples of each test, they were so close that I averaged them together, and that's why we ended up with 1 point here on the graph, even though we ran 2 samples. So the first thing you'll notice is that even with no collector metal, that little bit that we reduced out ended up with fantastic gold recovery and equally as good silver recovery. I mean, 99% silver and 99+% gold. So that went fantastic. The high surface area copper was actually even better. There was 3 nines recovery of the gold and 99.68% recovery of the silver. The copper bottoms did about as equally well as the no collector. The silver recovery here is a little bit low, and I believe that's because we had such a high amount of silver metal at the bottom of the crucible that we lost a little bit to the slag, either through oxidation or a little bit got tied up with some sulfur and was carried into the slag. So even though it looks like our silver recovery is really low, there wasn't much silver in the initial assay or in the initial material. And because we added so much silver, I think we lost just a little bit to the slag. The lead, again, did about as equal with the copper and then the no collector. And then this is the results from the Chapman flux, the one that I did kind of after the fact, just to see if we could oxidize away all of the metal and be left with a precious metal button. And as you can see, it didn't work very well. We only recovered about 80% of both the gold and silver. So this one proves that we do need a collector metal. You can't just try and oxidize everything if you have a fairly low grade of concentrates that you're trying to smelt. The other thing that I want to talk about here is even though we added different metals at the bottom to act as a collector, the process that went on with this no collector occurred in each of these tests. So now I'm actually concerned. This raises another question. I didn't realize the no collector would be such high results. And so regardless of how well the other metals did as collectors, this process happened in each test because this occurred regardless of what metal we put in the bottom. Okay, so here are the assay results. I wanted to show them to you guys so you can check my math and give you all the data here. These are the sample IDs down this side here. The first, number 1 and number 2, are the shaker table cons. That's right off the shaker table. That's the stuff that we were smelting. Number 3 and 4, no collector. 5 and 6, high surface area copper. 7 and 8 were the copper bottoms, silver bottoms, lead bottoms, the Chapman flux, and then number 14 isn't applicable to this experiment. And so they did 2 things. They did a fire assay here for gold and silver, and if the value that they came up with was less than was detectable by the fire assay, they came over and they did an ICP finish. And these are in parts per million, and which I believe equates to grams per ton. We can have some lively discussion in the comment section about if parts per million is equal to grams per ton, even though it doesn't take into consideration the density of the thing you're measuring. It's just a counting technique, essentially. But anyway, that's how I did it. I equated these all to essentially grams per ton. So the shaker table concentrates, we ended up with, the first one was 872 grams per ton, and the second one was 846. So I took these numbers, and I will show you a calculation by how I went from grams per ton to percent recovery. And one more thing I'll point out here is they actually ran a couple of duplicates for me. So this will be important in our next calculation. I'm going to average 3 of the numbers together. So this is a duplicate of the shaker table concentrates. So I'm going to average these numbers in with the first 2 to get the average amount of gold in our sample we started with. All right, so the first thing we have to do to determine our percent recovery is figure out how much actual gold we're dealing with. And so these are the assay values in parts per million of the gold and the silver in our shaker table concentrates. And so I took all three of these values and averaged them together. So average there was 863 parts per million gold and 1891 parts per million silver. Then we take that number, and because I added 100 grams per charge, we take 100 grams in tons, because this is parts per million. So you got to get it into how many grams of gold were in the sample. So you multiply by 0.0001, and that ends up with 0.0863 grams of gold in our original sample. So that's how much actual gold by weight was in our charge that we put in each time. And same thing with silver. We had 0.1891 grams of silver in our original sample. So now that we know how much gold we had and how much silver we had, we can do the same calculation for what was in the slag, and then you can divide the two together to get the ratio. Okay, so here is our sample calculation of how we ended up with percent recovery. So that we're gonna run our no collector sample. This is sample number 3. The assay for the gold was 1.31 parts per million, and assay for silver was 10.1 parts per million. And the slag for this particular sample weighed 260 grams. So we take our assay value for the gold, multiply it by the grams of slag in metric tons, and we end up with the amount of gold in the slag. So we end up with 0.0003406 grams of gold in the slag. And then you take the grams of gold in the slag, divide it by the amount we calculated just earlier, the amount of gold we started with in our sample, and you end up with 99.61% recovery. And the same thing, same process for the silver. One more number you guys are going to need if you're going to check all my math is the weight of the slag. And so I just wrote them out here. This is the sample number and this is the weight of the slag. So I'm not going to talk. I'll just go through this real quick and you guys can pause and then get all the grams of the slag if you want to check my math. And the only one that's different here is the one on the bottom. This is the Chapman Flux one. I added a lot more flux to that one, and I only used 50 grams of shaker table con. So be careful if you're going to do the math on this one. This is half the amount of shaker table cons and quite a bit more flux.
So as you can see, I have some more work to do. I need to refine the process so we're getting that super high percentage recovery of gold. And I have some ideas, so stay tuned for a future video and be sure to subscribe if you want to check out more videos like this one. So I hope you guys enjoyed this video. Thanks for watching, and we'll see you on the next one.